Hello everybody and welcome to your video notes on quantitative energy storage with elastic potential energy. So the learning target for this one reads, so this is the extends level for learning target 6.3, and I can use the kinetic energy, potential energy, and the new part is the elastic energy equations to set up a conservation of energy equation to solve for height, velocity, work, or spring compression. Okay, so really everything that's at the meets level is present here, but in addition to that, we're also adding in spring compression. So, and the elastic energy equation. So, what's the elastic energy equation? Well, some of you have seen this already, but the equation is the energy in the elastic account. There we go. Is 1/2 k x squared. This looks really similar to the one for kinetic energy, which is 1/2 mv squared, where m is for mass and v is for velocity. Well, for elastic energy, or elastic potential energy, I'll probably drop the potential energy and just say elastic. The k stands for the spring constant. And we'll talk about what that actually is here in just a moment. And then the x stands for the distance the spring is stretched or compressed. Okay, and this is the one that you would solve for, and the K, or the spring constant, will be given to you. And the spring constant is really, let's go to a different color. Spring constant is how springy the spring is. If it has a higher K, that means the spring is more rigid, meaning that it's harder for you to stretch or compress the spring. And if you have a lower K, that means less rigid, or you'd have like a flimsy spring. Okay, so we have how springy the spring is, or the spring constant. And the spring constant, the units are, it's a different color. The units are newtons per meter, or just N over M. And then the distance of the spring is compressed without, that's just meters. Okay, so here's the basic equation. And then the question is, well, how can I use that in a problem? So here we have the example that I'm going to use for this. The example says, how far must a spring be compressed? So that's what we're going to solve for. We're going to solve for x. To move a box across a frictionless surface at a speed of 25 meters per second if the box is 76 kilograms and the spring constant is 100 newtons per meter. So the first thing, just like previously, that we're going to do here is we're going to do an LOL diagram. Remember, we're going to solve for x. 25 meters per second is the velocity. 76 kilograms is the mass, and 100 newtons per meter is the spring constant. That's just for future use. So our LOL diagram is going to be, so if we say that all of this is our system, so we've got the spring and the box in our system, we've got elastic energy at the beginning. And in the end, we just have kinetic. Okay, we end up with the equation EEL equals EK, because if we say that a spring is in our system, then nothing gets transferred in or out of our system. There's no collision and there is no friction. So we end up then with going to the next step, which is substituting in our real equations, which are our elastic energy equation that I just told you is 1/2 times k times x squared equals 1/2 times mass times velocity squared. Okay. And over here, I have all the variables, or everything that we need to substitute in. So I'm going to go ahead and do that now. While I substitute in, feel free to jam to the music. Woo! And there you have the full equation. And just like before, when we solve these problems, they're a little bit longer, so, and the units get a little bit wild. So we're going to drop off the units now, and watch as I'll just go through and solve the rest of the problem. I went back and I calculated this little bit right here, put that in, and in the end I end up with 21.8 if you round, and then the units for this are supposed to be meters, and if we go back we could calculate those units as well, but our answer should be 21.8 meters, which is ridiculously large. But that's the answer that would be given these numbers. And there you have it. Thanks for listening.